So this is going to serve as kind of an introduction to what I hope will be a few series of lectures on the specifics of split testing. So if you want more details on some of the methods, because I'm going to do a survey here, come to the next few talks. Those are sort of the advertisements for that. Please ask questions as I go. I'm more than happy to answer them, and I'll stay after and ask questions and go for drinks and so on. So to get started, why do you actually want to run a split test, right? Why run it? So the first thing is you want to establish what's called causality. So everybody here probably knows about correlation versus causation. And what you'll see a lot of times when you're not running a test is someone will say, well, we pushed this change to the landing page and afterwards signups went up 3%. So it must be because of this change we made. But it could also be that it's a Tuesday and more people happen to sign up on a Tuesday than on a Monday, and that's the change you're seeing. Or web traffic went up, whatever it is. So the point of a test is to actually say that the change you're seeing is from, like the behavior you're seeing is from the change you actually made and should generalize going further, which allows you to say that because we made this change to the landing page, we actually expect, at least for the next while, that we'll get 3% more signups or whatever it is that you're testing. The next bit is you want to remove the guesswork from changes. So at POF, this was kind of a big thing. We were making a lot of changes where we would push stuff and then things would go up and down and we weren't really sure what was happening. Or it also didn't allow us to say that these types of changes, so adding icons, changing colors, things like that, what are the most effective things to do? It removes a lot of that guesswork. Sort of the knock against testing is a lot of times you're playing with very small numbers. So you might just be going for a couple percent or 5% increase. And if you're especially a larger company that's more established like POF is, it's very hard to get like a 50% increase unless you do something really, really drastic. Smaller startups, things like that, you might see that kind of behavior, but small changes add up a lot. So in the last few while, like we've had a few tests in a row that have done like 2, 3, 4, 5% relative change on, let's say, revenue. By the end of the year, you're up 20%, which 20% more revenue for how much we're making is a lot of money. The other thing that I think is very important to me, at least personally, is you democratize the process for product changes. So what I mean by that is it's no longer, I have more experience, my idea is better, your idea is not. Or, someone pushes forward an idea and then someone else who's in charge doesn't like it and it doesn't make it onto the site. In this case, it's everybody can come up with ideas, you test them, the ones that work stay on, the ones that don't, and that's kind of it. And the flip side of that is also that if you had an idea and it didn't work, at least you have evidence that it didn't work. And it's not just that you're pissed at your boss that for some reason he didn't like your idea or something like that. The last two things is you can document causal trends in the data for future evaluation. So this is kind of like where you'll have secondary performance indicators and things like that. So if I'm running, let's say, a registration test, my primary KPI or key performance indicator might be the number of people that sign up. But my secondary one, that's not what I'm judging the test on, but I want to look at later on for analysis, is the number of people that purchase an upgraded membership or something like that. So what we can do is still document the causal trends in those secondary things, and that gives us insight for future tests, future changes to make for the site. And the last thing, does everyone know what a HIPPO is? So it's highest paid person in the room or office or something like that. So you remove that. If anyone's ever been in that meeting where someone just says, well, I've been here 6 years and I make way more money than you, so like my answers are right. You remove that because, and this has happened, that person oftentimes doesn't propose the right change. Sometimes they do, sometimes they don't. So you kind of remove that entire thing from the process. And so everyone sort of feels much more empowered at the company. Okay, so what is actually a test? So a test or experiment, it's comprised of a few things. The first thing, and this is really important, if you're going to do a rigorous test, you need a single clear metric to judge it on. So you can't be like, well, we care about signups, but also the number of views on the page and also the number of people that upgrade and the number of people that do this, but we also don't want to hurt like something else. That doesn't work because then at the end of the day, you're going to have 6 different things. Some are going to go up, some are going to go down. you have nothing. So every experiment you design should have one clear thing. It doesn't mean that you don't look at other stuff in post and you can't consider them. But when you're actually designing the experiment, you want a clear yes or no sort of decision rule. The next thing you need is, and this sounds obvious, but you'd be surprised how little this is done, a reliable way to collect the data for the metric. So what I mean by that is if you care about conversions on the landing page, then you can't just look at total signups. You need the number of people that see the landing page, right? Because you need to be able to compute that conversion rate, and you better validate that data that you're not dropping 20% of it, or people that are coming from, Nebraska aren't being counted or something like that. So it's very, very important to have that reliable way to actually collect it. The next bit, and this is very subtle, is you need a controlled way to split the data randomly. Okay, now I'm in the right place. So what I mean by that is you want to make sure that your A group, your B group, and however many other groups you have are random over any confounding variable. So an example of a confounding variable might be someone's gender. So if you have the A group is all men and the B group is all women, and you're going to push the change to everyone, then that's not really a really well-defined experiment. You're just going to find out how men and women behave irregardless of the change, which is going to be folded into that, and you can't extract what's going on. The other thing is people say, oh, well, I know a way of randomizing things. I can take, profile or user ID, and I can divide by 2 in mod, right? So all the evens go in one group, all the odds go in the other group. That's completely random based on how people sign up. I'm good to go. The problem with that is that the second you run more than one test, those groups are identical. So if myself and Same are in the same group in test 1, because we have even user IDs, then we're going to be in the same group in test 2, 3, 4, and 5, which basically means what you do is instead of randomizing, you actually create what's called herding behavior, where the same people are exposed to the same kind of roller coaster of changes all together. And that's not properly randomized. So you need a way that actually randomizes it. You can't just divide by user ID. You can't just be like, well, I can do user ID this test and profile ID the next test, and then sign up time the next test, and then go back to user ID. It has to be really randomized, and that has to be controlled. The last thing, and this is the most important, is you need before you start the test, you need a clear decision rule. In other words, when X condition happens, I stop the test and I say this one won or this one didn't. You can't start running the test and then be like, I'm just going to kind of pick a metric, but I said I was going to care about a 5% change, but now I care about a 3, but I care about a 2, but I'm going to change my confidence level. And this one's kind of moving up, so good enough, I stop. If you do that, you will massively bias yourself towards certain results. So before you start the test, whatever the decision rule is, and we'll go into lots of different decision rules in a bit, you have to pick something, and everybody has to agree on that. I can't emphasize how important that is. And this is coming from mistakes that I and we have made. So the outline of this is I'm going to give you a few sort of methods of testing and splitting traffic and things like that. So I'll start out with what everybody knows is the standard split testing thing, which is null hypothesis testing. We're actually not really doing that very much at POF anymore. We've moved on to the thing I'll talk about last, which is more advanced Bayesian methods. So I'll tell you about what the basic idea of null hypothesis testing is. Again, I'm going to give a really rigorous talk only on null hypothesis testing. So for the people that want to know all the nitty-gritty math and things like that, come to that talk as well. I'll tell you sort of the pros and cons of it, and then I'll tell you how to scope and run a test and all the sort of pitfalls and mistakes you can make. And then I'll tell you about these other methods. So NHST, null hypothesis testing, is you basically have 2 hypotheses in the simplest version. So you have what's called the null hypothesis, which is the thing you want to test for, and then an alternative. So if we're doing an example, then the null test is, let's say we're doing a landing page and we want to improve the number of people that are signing up from the landing page, the conversion rate. So the null hypothesis is that whatever change I made had no effect and the 2 pages perform exactly the same. The alternative hypothesis is that there's a difference between the 2 of them. And all that a null hypothesis does is tell you whether or not you can reject the null. So it just says the null is, again, these 2 pages are the same. It's just saying, are they the same or are they not? That's all it tests for. basically the rejection is saying like the variant is performing differently. So there's a couple of different kinds of errors you can make, and I thank Charles for this awesome slide. So there's what's called a type 1 error. So the way to look at this is stretches. So up here is, imagine you were like God or something like that, and you knew the actual underlying truth of the situation. So in other words, the null hypothesis is valid or it's not, right? If you had perfect data, took an infinite amount, that kind of thing. Then you have what the test is actually telling you based on some statistic or something like that. And so in these corners, you have the correct outcome. So in other words, if the null hypothesis is true and the test fails to reject it, that's good, right? That's a true negative. If, on the other hand, the null hypothesis is not true, there's a difference between the two pages, and the test rejects it, that basically means you've got a true positive and you're good to go. Everything else is an error, and there's two types of errors. The first one, which is the false positive, is basically telling a guy he's pregnant, right? So that is, the null hypothesis is valid. The two pages are actually performing the same, but for some reason you've detected a difference and you're saying they don't. What that means, if you're a company or a data scientist and you're pushing this change, it means you've detected the change, you've gone to your boss and you've said, we're going to see a 5% increase in signups. They make the change and nothing happens. That's what that means. The other one, which is a type 2 error, basically means there is a difference between the pages and you have missed it. So that basically means you go to your boss and you say, nope, pages are the same, don't make the change, and you've just missed out on 5% of signups increase. So a lot of testing is about understanding what these errors are, bounding them, and not biasing yourself towards one or the other. Okay, so here's how you actually run the test. So the first thing you need to do is establish a baseline rate. So let's stick with the landing page example. So in other words, I need to know that my base landing page conversion rate is 65%. So 65% of people do that. What you want to do to get that baseline is take it over one business cycle. So at POF, the smallest business cycle we usually have is a week. Why is it a week? It's because, as you can imagine, people on a dating site behave very differently on a Sunday than they do on a Tuesday. We also send out things like promotional emails on Sunday and Wednesday and so on. And you can actually see, if you plot any metric we care about, signups, messaging, all that kind of stuff, it looks like an EKG machine over the week. So you want to make sure that you're not capturing way more traffic or different behavior, things like that. The other thing you want to avoid is, like, we get a huge spike at things like Valentine's Day and Christmas and New Year's. Don't take your baseline then, because that is not representative of what is normal behavior on the site. So you want to make sure you take it for at least one full business cycle so you actually see that kind of behavior. And what a business cycle is requires domain knowledge and knowing your business. So that's the kind of thing where for us it's a week, for other people it might be an hour, a day, a month, whatever that is. Then you basically bound your errors. So you say, for example, I want no more than a 5% false positive rate and no more than a 10% false negative rate. You can pick whatever that is. It's whatever you are comfortable with as a business. Once you do that, you compute the necessary sample size. Both bounds weigh into that. A lot of split testing calculators online that I've seen only care about the type 1 error, the false positive, and they don't correctly bound the type 2 error, the false negative. If you don't do that, you're going to get it wrong. They like to do that because if you don't correctly bound the type 2 error, your necessary sample size is way lower, and you think this is great because I can run the test 4 times as fast. You can't. You're just going to get it wrong that much more often. So in this in-depth talk, I'll actually go into the math of how you actually compute that based off a test statistic. Again, you run the test for a whole number of business cycles. So there are times when we've had things where the necessary sample size will accrue over 2 days, but you still have to run it for a week, because if I just ran it for the 2 days on the weekend and then I push the change, well, then the other 5 days of the week, people might behave very differently, and I haven't correctly done that. So there's no like hard and fast rules here. It's all about kind of trying to bound your uncertainty as much as possible and get the generalization once you actually make the full change to be as true as possible. So you basically run it, and then once you actually have the necessary sample size, you check the actual sample size, not the results. You basically say, okay, we're going to stop it, and then you figure out the results. And normally that's usually expressed in a p-value for a null hypothesis test. So what that is basically this. So you say the p-value basically measures how likely you are to see a change at least that large by just random chance. So like, let's say there's that 5% change in signups. If my control and my variant page were exactly identical, how often would I just see a random 5% change just because the group happened to be 5% different, that kind of thing. It's not a confidence interval. People report it as a confidence interval. If somebody says, our p-value is 0.05, which is like the one minus that is 0.95 or 95%. That is not a 95% confidence interval. It's not even close. Don't report it as such. If you want to report a confidence interval, there's ways of calculating that, but it's not a p-value. It's not a probability of the result. It's not saying if your p-value is, again, you get a 95% size, it's not saying that you have a 95% chance of anything. It's nothing. That people that say that, it's meaningless. Generally speaking, the decision rule works if the p-value is below your threshold for false positives. So you said I cared about a 5% false positive rate. The p-value is 0.04. You're good to go. You call it, you reject the null, and you say, I'm going to make the change. If it's greater than that, so it's like 0.1 or 0.4 or whatever it is, you say, nope, I can't detect a discernible difference between this. Stick with the control. So let me talk a little bit more about p-values just so you understand what's going on. So let's say we have a p-value of 0.05 for, I guess I picked a 10% relative change. So what that means is, let's say I had two identical pages. If I just ran 100 experiments with the necessary sample size, we basically expect 5 of them to show a change at least as large as 10%. Some might show 15 or 20 or something like that. And you can see when you express it that way, that is not a confidence interval or a probability or anything like that. So it's important to understand that. And for your business or whatever decision you're making, to understand that that's the risk you're taking. Okay, so pros and cons of this. Statistically speaking, and of various tests and things you'll see, it's pretty simple and straightforward. It's a well-defined thing. People have been doing this for hundreds of years. It works in a variety of situations. So I talked about landing page conversions, but you can do this in lots of different scenarios. You can extend it to lots of different variants. So if you don't want to run an A/B, you want to run like an 11 variant test on your landing page, you can do that. You can do it to non-conversion based things. I say easily because the more complicated and the more you move away from conversion based things, the much cleverer you have to be about phrasing, like knowing your distribution, guessing the statistic, and getting that right. This is kind of my opinion. One of the reasons I like it, it's easy to understand. And once you understand what a p-value is, it's very easy to communicate the results to non-specialists. And you can phrase that. You don't get into complicated things about multi-arm bandits and things like that. It's just like, you've got a 5% chance of getting this wrong. And people understand that. And then they can say, we're comfortable about this or we're not. The cons about this are you have to set your test durations in advance. So let's say I scope for that 5 or 10% relative change. And, the third day I'm looking at the test, it says it has to run for 10 days. The third day I'm looking at the test, it's actually a 25% change. You cannot stop the test early. We'll go into a minute why you can't do that, but you cannot stop it early. So that has a lot of implications. At least for us, one of the reasons we move to other methods is we do things where we test on revenue-based things. And so if you're seeing a 20% increase, you want to push that change out as fast as possible because that's money you're leaving on the table. The flip side of that is if you're seeing a 20% decrease, you want to stop the test, right? And the problem with a null hypothesis test is you cannot do that. Anything you do that way, you bias your results. So how to screw it up? So if you basically, your decision rule is, I'm going to keep running the test, and the second I see a p-value less than 0.05, I stop the test and I call the winner. So can anyone see what the problem with that is? I'm actually asking, does anyone see the problem in that? Someone? Exactly. Yeah. So basically what will happen is if you look at this, the thing will fluctuate around, and at some point, probably, it's going to dip down where the p-value will dip down below 0.05 and you'll call the test. It's going to go back up again at some point. So if you literally and this sounds really stupid, but sometimes people do this. If you basically will say, I'm going to run the test for an infinite amount of time until significance is achieved, you've guaranteed to always get a significant result, right? Which is clearly wrong. Now, anything else you do that's not that, but is some direction like towards that, is just biasing yourself towards getting a significant result when you shouldn't. So you can be like, well, I'm only going to check 5 times. Yeah, that's better than checking, every point, right? But that's still biasing you. So everything you do there is making it worse. So every time you check, you basically bias yourself towards type 1 errors. So I kind of stole this idea off Evan Miller's blog, which is a really good blog to read if you don't know it. So let's say we're going to do this and we're like, well, we're only going to check twice. And I'm going to check, let's say the test is going to run for 1,000 observations. So I'm going to check at 200, 500, and 1,000. So I'll check 3 times. So at 200 observations, this is what it looks like. And I'm going to do this the correct way first. So at 200 observations, I have 2 possibilities. It can be significant or insignificant. At 500, it can be insignificant or significant. And then I call it at 500. If you actually stop the test after 200, this one you've stopped and you've called it significant when it's not. And you can run simulations of this and kind of, for different levels of conversion rates and how many times you check and sample size and so on. People are like, well, I'm only wrong if I check twice, a few percent of the time. Sometimes you're wrong 30 to 40% of the time. And if that doesn't scare people, I don't really know what it is. If you're pushing the wrong change to a landing page or a subscription page 40% of the time, you are leaving a lot of money on the table and possibly actively harming your business. So stop doing that. The other flip side of that is there's lots of companies that do this. So if you're the one that doesn't, you're doing 40% better than they are, which is good. Okay, the next way to screw it up is you want to test on many variants. So you want to run a 10 test, you want to run a 10-way test or a 4-way test or whatever it is. So there's actually nothing wrong with doing that, and there's methods for doing that. The problem is that each pairwise comparison you do, so basically you say, okay, I'm going to compare variant 3 to variant 4, and also variant 3 to variant 2, and variant 3 to the control. Each one of those is an independent experiment. And we just said, right, if I pushed 100 identical pages and I tested them, that there's a 5% chance that, one of them is going to show a significant result. So the more checks that I do, the more likely I am to see just a significant result just because I've increased the amount of variance that I'm doing. So there's ways of accounting for this. This is called the multiple testing problem. And there's more sophisticated techniques that handle when you have many variants, how to basically unbias yourself from that result. The problem is many people don't do that. They just say, I'm running 10 variants. My p-value, I still care about a p-value of 0.05. And they do all the pairwise comparisons. And then lo and behold, one of them is 0.04. And they say, that's the winner. I've successfully done it. No, you have not done that. And you're, again, quite biasing yourself towards getting the wrong result. So the upshot of that is when you add the number of variants, it increases your runtime in a non-linear way. If words like combinatorics and NCP don't make sense to you, don't run a multivariant test, right? If the word Bonferroni doesn't mean anything to you, again, don't run a multivariant test or find someone that does. And this is also something I'll cover in more in depth in a later talk. To really screw up in null hypothesis test, do both, right? Run 27 variants, don't account for it, and check every data point whether or not you have a significant result. Sure, you can do that. And there's a lot of online calculators and things like that that do it. You will kill yourself. Don't do it. Okay, so let's move. The question was, what if the conversion rate is very low? So in some cases, yes. And that usually just means you need a whole big sample size. So yeah, we've had things where product managers come to me and they're like, we really want to test this. We're really excited about this change. And I scoped the test and I actually told them once it would take 10 years. So unless you're willing to not run another test on the upgrade page for 10 years, probably this is not the most cost efficient and productive test to run. So that's where like actually correctly scoping an experiment and making those decisions comes into play. So yeah, the lower your your baseline conversion rate is, the longer you'll usually have to run a test, because essentially you're looking for, even though I'm talking about relative difference, at the end of the day, you're talking about absolute differences between two curves. And so the smaller the baseline rate is, the relative difference between that small thing is a much lower absolute difference, and that kills you. Pick a different method, which we'll talk about, or don't run the test, right? Like sometimes you have to make the hard call that like, don't run the test. And we've done things like that where it's like, we just push the change, or we decide to shelve that change for a little bit until we have more traffic, or we redesign the experiment in a way that takes into account more samples. So instead of slicing on, only men, we might have men and women in the test or something like that, or different demos, different locations, things like that. So it's all about kind of playing with that stuff and making sure. And when you see a test that's going to take 10 years, don't run it, right? I mean, that's a hard reality. I wish I could run everything that they wanted to do. It's not a judgment. It's just, unfortunately, I can't make math go a different way. So that's the way it goes. So the next sort of more advanced method is something called sequential testing. So this is often used in medical trials. And the reason is that if you're poisoning someone, you want to stop. And if you've discovered a drug that cures cancer, you want to rush that out to everyone as fast as possible. You don't want to wait 2 more years to get necessary sample size. So what this does is it basically allows you to check your results at any time without biasing yourself towards false positives or false negatives. So you still have a null and an alternative hypothesis. This isn't Bayesian. This is still frequentist testing. And basically, the key difference here is every check now has not 2 outcomes, it has 3. So the null hypothesis test had 2 outcomes, significant or not significant. This one now has call for the variant, call for the control, or needs more data. And the key is that last bit. The fact that it has the ability to say needs more data removes the bias towards either false positives or false negatives. Okay, so here's how to do this. Again, I will give an actual talk on this. I have to kind of ramp through it a little bit quickly. So there's this thing called a sequential probability ratio test, or SPRT. There's a generalized version of it, which is GSPRT or something like that. So for people that know, what you do is there's something in probability and statistics called a likelihood function. You compute the log ratio of the 2 likelihood functions, and then you basically check that at any time. So you write down the likelihood function for the null, which is the 2 pages are the same. You write it down for the alternative, which is that they're different. And then you compute this thing. And at the end of the day, what you get is this kind of curve thing where above a certain line, it says call for the variant. Below a certain line, it says call for the control. And anything in the middle, it says you don't have enough data yet, right? And so what you do is, and you can actually watch this when you run the test, you'll see it kind of wiggle along, and then at some point it has enough data and it goes up or down. And these lines here and these regions are all computed based on your restrictions on the type 1 and the type 2 errors. So if you say, I want only a 5% chance of a type 1 error, a false positive, and I want only a 10% chance of a false negative, that tells you what those lines are. There's a straightforward way to compute that, and then you just run the curve and do that. So at any point, basically every time you take a data point, you check the ratio and you say either I need more data or you call a winner, and that's it. And that alleviates the problems with null testing in terms of requiring you to run to a sample size. So the good part of this is it has adaptable test duration. So if you scope for a 5% change, but it's a 37% change that you're seeing, this thing will stop way earlier. Right? And that's good, because if you're testing on revenue or signups, it means it's telling you right away you can stop and push the change to everybody, and you'll see those gains immediately. I'm not going to go into Diamond Pearson, but you can show mathematically that let me finish this and then I'll call on you. In almost all cases, this will run faster than a null hypothesis test. That is a not very non-trivial mathematical proof that relies on convergence theorems and stuff like that, but you can actually show that. Yes. The reason for that is, again, you want to avoid the thing that's going to take 10 years. So it's not that the runtime is dead on anymore. Like you don't know the exact sample size, but if you know it's going to run roughly like a null hypothesis test, but a bit faster. So if the null hypothesis test is saying it's going to take 10 years, yeah, this thing might finish in 9.5, but it's not going to finish in a day, right? So you want to still do that scope. So again, when you're designing the experiment, you have to pick a minimum change that you care about. So you have to say, okay, I care about a 5% minimum change, and anything less than that, I don't care about, or I care about a 10%, or this one, I really care about a tiny little 1% change. That's a choice you actually have to make before you start the test, right? If you don't make that, it's a sliding scale because everything depends on essentially how far apart two curves are, or the area under two curves. So you need to specify that before the test. Does that make sense? So the first con of this is, yeah, there's no way to exactly scope a test in advance. It's just going to run till it finishes. Most of the time, it will be faster than a null test, but you can't guarantee that all the time. What I often do when I was running this is I would do exactly what I said. I would scope the null and say, well, this is a good ballpark outer bound on how long this is going to run. Is that reasonable? And then kick off this test. There are scenarios, especially for very low conversion rates and things like that, where this will take longer than a null test. For most other things, it'll be faster. And when it is longer, it's not significantly longer, but it is a little bit longer. I'm not an expert on this, but extending this to multivariate is a little bit tricky because you have to compute many ratios and sort of see where they go. The other thing, so Felix, where's Felix? Felix and I had a huge conversation about this at some point. So, and it's also true for multi-arm bandits, which we'll get to. Large initial swings, if you have a lot of seasonality, so like POF, a lot of people are signing up on a Sunday because it's the weekend. That large swing could kick you up into the region and stop the test before like the full generality of results come in. So you need to be aware of that and possibly adjust for those errors. If you actually care about not just saying this page is better than that page, but saying like this page is 7% better than that page, you have to do quite a bit of fancy math to get that projection. The reason for that is because this stopping rule depends on the results of the test as it's running, it gives biased estimates in the technical sense. So if anyone knows statistics, the expectation value of the change that you're computing is not the true value. So you have to account for that. So that is kind of a complication. Most of the time you don't care because you just want to know if something is better than something else, and that's the important thing. Okay, multi-arm bandits. So multi-arm bandits they're not really a testing method. What they essentially do is dynamically allocate traffic to the better performing page or whatever it is. And that's based on the current performance. So you start them off all equal. One has a slightly better conversion rate to start out. It starts shifting traffic in that direction. Then that might maintain it or it might not. It might shift back and so on. So essentially, the problem arose with, and the reason I have a picture of a slot machine that's called a multi-arm bandit is, imagine you're faced with a series of slot machines, all of which could pay out at different rates and for different amounts. So this one pays out 1 out of 100 times you pull it, gives you $50. This one out of every 10 times you pull it, gives you $1, and so on. If I don't tell you anything about the slot machines and I give you $1,000, what do you do? Right? That's a well-defined problem, but it's not easy to solve. Let's assume you're a stupid gambler in Vegas. So what you do is there's two phases to this. There's what's called exploit. So exploit is based on your current knowledge, you've pulled a few times, you have some idea of what the best strategy is. So you want to play that best strategy. But you also realize that your knowledge is not perfect. So what you want to do is explore many other options. And what a bandit algorithm does is essentially balance in some way, based on your current knowledge, the explore and exploit phases. So there's lots and lots and lots of, actually Chasm gave a phenomenal talk on multi-arm bandits as they applied to advertising. And his talk was like an hour and a half and still didn't cover everything you'd ever want to know. There's lots and lots of different algorithms available for a multi-arm bandit. Essentially, though, you can think of each algorithm as just a different balance between explore, exploit. Some of them are a fixed ratio. Some of them decrease as you're running it and you get more knowledge. Some of them are Bayesian and so on. And you can sort of see how this runs. So you've done one pull. This one did better. And then as you do more and more pulls, your knowledge of the blue one over the red one, you can see that like this one is performing better than the red. So it starts shifting more and more and more traffic towards the blue until here you get to 1,000 pulls. And then it's like the blue one is the winner. Stop putting any traffic to the red. So there's not really a definite stopping rule here. You can have a stopping rule. You can make it up yourself. You can just sort of say, well, when most of the traffic is going in this direction, that's when I'm going to stop. That's my third con. Okay, pros. So it dynamically apportions traffic. So if you're doing revenue or landing page or something like that, if one of the variants is way better and is performing as such, you will reap the gains immediately, right? As soon as if this one is 20% better than that one, it's going to very rapidly start shifting traffic in that direction and you'll reap those gains. It's extendable to any number of variants. If you want to run like 65 at once, it doesn't matter, right? It's still going to eventually find the best one. So cons, the first one is a technical one. Because how you apportion the traffic depends on the results of the test, that means the entire thing needs to be fully integrated into your test architecture. So for us at POF, we get about 750 million events a day we're storing in BigQuery. That's a lot. And that's raw. So our test results are often very complicated, sort of denormalized things coming off those raw event tables. And that's not integrated currently. Like there's not a button you can click where like when a test is started that I can write select star from results table and just get the results of the currently running test. I have to do a bunch of stuff. So for that, we can't run a bandit right now, right? Because I can't rapidly get the results and feed that back into the thing that's randomizing and picking traffic and so on, and saying 60% of traffic should go here and 40% of traffic should go here and so on. So if you're going to go the bandit route and you're going to do this yourself, realize there's a technical hurdle that has to be implemented. That said, things like Google Analytics and stuff like this, I think there's a lot of things that automatically implement this, right? So it's very doable then. If you want to test stat out, so at the end of the day, you want to compute a p-value because it's not equally apportioning the traffic, it will take longer to run than a null hypothesis in general. Now to Charles's point. So the basic algorithms here that I talked about, they all assume that like the conversion rate on your landing page is constant in time or very close to constant in time. Like, yeah, if it goes from like 40% to 40.01%, that's not an issue. But it's assuming that it's not going from 40% to 20%, which for a landing page is probably reasonable. If you're in finance trying to do this with the stock market, it does not work. If the payouts are not constant in time, you move into a realm that's called adversarial bandits. And they're the theorems that show that you'll eventually converge to the right solution, and how long that takes become a lot trickier and runtimes become a lot longer. So if you're in a situation where you think the actual underlying base rate itself is very volatile, bandit might not be the way you want to go. The other thing is, much like any sequential thing, it can be sensitive to that short-term seasonality. So again, we kick this off on a Sunday, and all the people that are signing up really like this page. It starts dumping all the traffic to that page. But it's going to now take Monday, Tuesday, Wednesday, Thursday, Friday possibly to win out over that traffic because, by Monday, only 10% of the traffic is going to the other page. So it takes quite a long time to kind of tilt back to the right thing. So this can be sensitive to short-term seasonality. And when you start setting your limits for the bandit and the algorithm, you want to make sure you're taking that into account. So if you think you have a very seasonally dependent thing, make sure it doesn't immediately start dumping traffic. If you're confident that you're not, you can be a little bit less stringent on that. Okay. Bayesian. Everyone wants to go into Bayesian. Yeah. No, you can. You absolutely can. Right. And there are companies that do this. So you can be like, here's a landing page and I'm going to like keep introducing new variants and things like that. And you can absolutely do that. It's a question of how large the shift is, right? Because let's say on Sunday they like the red button, and because of the way you've tuned the limits on your bandit algorithm, 90% of traffic is going to the red. So by the time you get to Monday and it's like, well, all the people on Monday like the blue button, but you're sending almost everyone not to the blue, it takes a really long time to swing back. That's a very, very extreme example, but it takes a long time. Does that answer your question? Yes. So you can do what's called batch bandit, or I think that's what it's called, where instead of updating the bandit with every run, you're like, I'm only going to update it every day or every week or so on. So all of that is available to you. And that is one way of combating that seasonality. The downside to that is, like, let's say I'm only going to update it once a week, it will take that much longer to find the best solution. So it's kind of a balance, and there's no like, you know, pick a value of alpha zero point zero 0.03 and you're good to go. You have to kind of guess it, and there's a little bit of an art to it. Um, but yeah, so you can get around that kind of stuff, and we've talked about doing that as well. It's also, we've talked about doing that so we don't have to do 750 million events every, 3 seconds to get the results of this thing and feed it back into the test plan and so on. So that's another reason you might want to do it. Oh, sorry. The question was, instead of updating it with every data point to combat the seasonality thing, can you just choose to update it at fixed intervals? And so, yeah, my answer is yes, but then it will take that much longer to go back to the right solution. So I'm going to tell you 2 ways to do Bayesian testing. The first one is the way you read on everybody's blog. The reason I'm going to tell you about this is it's just wrong. And I don't know, like, don't believe everything you read on the internet. Even if it's coming from a place you respect, this stuff is on Evan Miller's and somebody else's, Chris Stuccio's blog, as the way to run a Bayesian test. And I read it and I started doing it and I just kept getting wrong results. So this thing basically says the same thing. You basically have two hypotheses. The first one is, again, the 2 pages are the same. The second one is the 2 pages are different to some amount, 5%, 10%, and so on. And you can put prior assumptions on the 2 hypotheses. You can say, well, I think there's a 70% chance that they're the same, and I'm going to put that in. Most of the time, you just say they're 50-50 because you don't want to bias yourself to begin with. And then what you do is essentially compute the Bayesian posterior probability for the null hypothesis and the alternative hypothesis. You see which one is bigger, and then you convert that into a probability. And then usually you say, well, if the probability that, this one is bigger is 95%, then good to go, I call the test. So the pros of this is that it's intuitively interpretable results. The probabilities are actual probabilities. You can check the results anytime you want. It's a sequential test. You can shift them around. You can be like, well, now I only care about 80% confidence. You can do that and you don't bias yourself. You can extend it to any number of variants you care about, and it's all good. The downside is it's just wrong. Like, the reason I say it's wrong is we ran simulations of this and other methods, and this thing was wrong like 40% of the time. Like, it's not a little bit wrong. It's just wrong. The stopping rule is just really poorly defined. The reason for that is it's a point hypothesis, right? It's just some number is like 92, 93, 94. Nope, no, it's 95. Stop the test. And because you're running it sequentially, it's super, super sharp. There's no way to scope the test in advance. This is a normal problem with this kind of stuff, but it's just like the test runs till it's done. If you want to do things so non-Bernoulli is non-conversion based stuff, the math gets a lot more complicated. That's not an impediment if you know how to do the math and you're comfortable with saying words like Markov chain Monte Carlo and stuff like that. But otherwise, it gets a lot tough. The prior choices here where you say, oh, well, 50-50 versus 70-30, and also what distribution you think they're going to follow, it's very, very sensitive to that. Yeah, don't do this.
All right. Okay, cool. So what does it mean on the pro side? Results can be checked at any time, but then at the same time, there is no way to scope a test duration in advance.
Okay, good. That's a really good question. So remember when we did the null hypothesis test? That one I would say you could scope it and be like, here's my necessary sample size. What I couldn't do in the null hypothesis test is be like, well, I'm halfway there. I want to check the p-value and stop it, right? If the test is significant, because that would bias us towards a certain result. In this case, at any time you can check the results, and the second it's significant, you could be like, I'm stopping the test, and you won't bias yourself one way or the other. So that answers the first bit. The second bit is because I can do that, I can't tell you exactly how long the test is going to run. So does that answer your question? Okay.
I'm not defending those guys. I don't know them. I don't know the law. But it sounds like my textbook definition of doing Bayesian won't fit that. So
Yeah,
my
it's
guess is they write that assuming that you're doing not conversion testing. You're just saying
no.
have any ongoing thing. I'm just looking at a block of data and looking at those probabilities.
No, so where you're getting it wrong is the decision rule. So the probabilities and the odds ratios, those are all correct things. The decision rule doesn't properly, like, it's an improper cost function. And so what you think is like, I'm bounding by a 5% error, you're not. And because they haven't phrased it in a proper Bayesian decision theoretic context, in actual decision theory, the rule is ill-formed and you don't get the right answer. So it's really just that what you think are your bounds on false positives and false negatives are not what they are. Whereas when I talked about the sequential probability test, those regions that I defined are rigorously defined in terms of the type 1 and type 2 errors. And where this went wrong is I actually went down a cul-de-sac where I was reading this on a couple people's blogs and I started commenting because they had what looked like a cost function, but it wasn't quite correct. And my hope was when I was learning this stuff is, oh, there's some small mistake I'm not understanding here. And I'll comment on this guy's blog. The math all looks really good. And he'll just tell me the answer. And he kind of told me something that didn't really make sense. And then I followed it up. And it's been 6 months and I have yet to get a reply to the second one.
So they're really
In this case, they're talking about conversion testing. Yeah, because the example they use for people that know this thing uses a beta prior. So for Bernoulli trials, the pull from a beta gives you a Bernoulli distribution. So they are using a beta prior and they are computing the posterior correctly. And what they're essentially doing for the decision rule is doing the integral over the posterior for probability, like for the conversion rate of 1 to be greater than a conversion rate of 2 by some minimum distance. It's the decision rule that's wrong. So what I'm about to tell you is a better way of doing this. Yeah. So what you can show is that the pull from a beta is essentially a Bernoulli distribution. And you know that for conversion-based tests, which are essentially coin flips, that's a very good approximation to it. Also, it's really easy to work with a Bernoulli or with a beta prior because it's conjugate to itself. What that means for people that know Bayesian is that when you have a beta prior, the posterior distribution for that, given all the data you have and so on, is also a beta with just updated parameters of the beta distribution based on the number of successes and failures that you have. So the number of heads and tails essentially you flipped. And so you can very quickly write down what the posterior is and the posterior distribution and compute the answer. If you didn't assume that, which I actually don't for some things in a slide or two, then you have to do like some kind of like Markov chain or Gibbs sampling or something to get the posterior result. And that is much more computationally expensive. And then you have to be familiar with those techniques where if you pick a beta prior, you can immediately write down the answer. So the question was, how off would you be by choosing a beta prior, as opposed to choosing what you think based on your actual prior knowledge is the proper distribution for the prior? There's no hard and fast answer to that. For conversion, it's usually a good assumption that it's going to be a binomial or Bernoulli trial, and then the beta is really good. And then it's a question of like how uninformative a prior do you choose, like how flat a prior versus like how peaked it is and what the width is. If for some reason you have reason to believe that it's not Bernoulli for whatever reason, and there are lots of things that are not Bernoulli. In fact, everything that's not Bernoulli, which is one thing and a lot of things, is not Bernoulli. Then yeah, you're going to be off. And then the question of how off you are is how off the underlying true distribution is from a Bernoulli. And that's a context dependent question. So like if you really have like a gamma distribution or a Poisson distribution, you're going to be way off, right? If you have something that's really close to that, especially for large sample sizes that goes over to a normal or something like that, you'll be pretty close. So it's hard to sort of pin that down one way or the other. The best thing you can do is pick the thing you think is best. And we do that a lot. Like when I'm working with this at PUF, there's lots of things we test that are not conversion based, like explicitly not conversion based. We spend a lot of time trying to guess what the prior distribution is, taking data, plotting the prior distribution off that and seeing if it fits. So we do QQ plots and fit tests and things like that. And we pick the best thing we can. Does that answer you? Here's the right way to run this. So what you first do is, let's say you have 2 landing pages and you want to compute the difference in conversion rates. So what you want is not the posterior for landing page 1 and landing page 2. What you actually want is what's called the joint posterior for the difference in the conversion rates of the 2 pages. So you want like conversion rate 1 minus conversion rate 2. And you want to see if that's greater than 0 or not. So what you do is you have to compute that joint Bayesian posterior. I can't do that in 5 minutes, but you can do it. The way you do that is, let's take the simplest example where I have a beta prior. So for each landing page, I know they're independent and I have a beta for each one. So I have the Bernoulli. What I can then do is simulate a whole bunch of draws from those distributions. For each one, I have conversion rate 1, conversion rate 2, subtract it off. I do that 10,000 or 100,000 times, and I plot a histogram of that thing. That's an approximate distribution for the Bayesian joint posterior. So again, now you have to actually run a Markov chain Monte Carlo. In this case, we do it by Gibbs sampling. You can use other techniques if you want. So what you do is you run the test, you start collecting data, and you start updating your posterior distributions. So again, for conversion, use a beta prior because it's easier. Not conversion, learn Markov chain Monte Carlos. You run it again for at least 1 business cycle. Anytime you want, though, you can check the results. So what you do is you simulate this, you compute the posterior for the difference of the 2 rates, and then the decision rule is framed this way. So there's 2 numbers you care about. The first is what's called the highest density interval, which sounds complicated, but it's not. It's essentially asking, where is most of the mass of the curve? So if I look at this bell curve, which is an actual experiment we ran on one of our upgrade pages for conversions, you can see that most of the mass is in the center. So let's say I care about confidence to 95% level. I ask, where's 95% of the mass of that curve? So you just numerically integrate it, find where the center is, and do that. The next number you care about is called the ROPE, which stands for the region of practical equivalence. That's the minimum change you care about. So if I care about a 5% relative change, anything less than 5%, I just say that's equivalent to 0. That's my region of practical equivalence. So the first thing I do, the first check I do is I want to make sure that I have enough data that the curve is narrow enough that I'm not early calling the result. So what you say is, I say, what's the width of this 95% ratio in this case? And how does that compare to the width of the minimum change that I care about? If that ratio is small enough, I think in our case, we usually use 2 because in practice, that was kind of the best balance between how fast we wanted it to run and accurate results. Then I move on to the next part of the rule. If that ratio is too high, in other words, the curve is still too broad because I don't have enough data or the data is wildly swinging around, then it just says, you need more data, keep running the test. On the other hand, as this curve gets narrower and narrower, essentially what's going to happen is either the whole curve is going to be, or the majority of the curve is going to rule out 0, or is going to rule out the minimum change you care about. If it rules out 0, call it for the variant. If it rules in 0, call it for the control, and that's it. There's some subtlety edge case stuff, which we'll get into in like when I actually talk about this, but that's essentially the concept here. I admit it's a lot I'm throwing at you. It's not the simplest thing to run, but it's extremely powerful. So here's the pros and cons. So again, it's intuitively interpretable. The probabilities are actual probabilities here. So if I say, with 95% confidence, this is performing better, I really mean 95% confidence. It's not a p-value. It's not some weird thing there. Any second you want, you can check the results. So it has all the advantages of a sequential test. The other thing is you can slide things around. So you can be like, well, I was caring about a 5% change, but I want this to stop a little earlier. So now I want to check for a 10% change. You can do that and you will not bias yourself. So you can kind of make those decisions on the fly, which is really nice. As you start seeing the data, you can kind of change your mind on things. The decision rule is clear. I've coded this up myself. It's in a package I made for R. Every time you feed it something, it spits out stop or continue, and that's it. So it's a very clearly well-formed decision rule, and you can slide it around given all the intuitively interpretable things you care about. That's a mouthful. So you can be like, well, I care about this minimum change. I care about this confidence level. You can slide all those around. The decision rule adapts to it perfectly. You can run this on any number of variants you want. Extending it to more variants, you do have to solve the multiple testing problem, but you can totally do it. You can do this, forget about conversion rate stuff. If you can reasonably guess some prior for something, you can run this. So we're running this right now on revenue at POF. Revenue is complicated for us because on our upgrade page, you have 3 plan choices. So you can pick like a 3-month plan, a 6-month plan, or a 12-month plan, but you can only pick one. So the choice is a dependent variable. In addition, the price of each plan is not the actual return you get because people renew, they upgrade again, and so on. So we have a whole curve for the expected lifetime value of like the 3-month membership with an uncertainty, and it's actually not symmetric and so on. That has to be folded in as well. So it's actually a very complicated Bayesian graph model that you have to do and simulate multiple things. That said, we can do it. We do it all the time. And you can actually be like, well, we expect this page to make 6% more dollars or whatever it is, revenue per user visit to the upgrade page. And you can test on that. And we do. So the cons, officially there's no way to exactly scope a test in advance. That said, there's various approximate methods you can do by either running simulations or outside ballpark. You can run you can scope it for if it was a null test. That said, most of the time we've run the simulations, it finishes in roughly half the time of a null. So you can run tests roughly twice as fast on average. The two main complications are if you have a very complicated model where the prior choice is not simple, it can take quite a long time to run the computation. So there's one test we're running right now that depends on what's called a negative binomial prior. That thing is just hard to compute. It's hard to simulate. It doesn't converge fast. The downside to that is we have to run for quite a while to actually get the result. But for most things, it returns quite fast. For like, if you're doing conversion on a landing page, it will return in like milliseconds. So it's not a problem. The other thing is you need someone that knows what you're doing. This is not like someone that's read an intro stats book and kind of knows what a p-value is cannot run this. So you do need to have someone that knows what they're doing or find some external package that does this for you. So, but that's really the only cons. It's kind of got all the advantages you want. You can check anytime you want. It's faster. It's more accurate. And you can extend it to anything you want. So you look at it, the way you pick a prior is the way you do it for any Bayesian thing, right? So you take a whole bunch of data, you look at what the curve looks like, and then you guess. And you try to guess as best you can. And then if you're worried, you try to make it as uninformative as possible. So for people that don't know, an uninformative prior is basically saying like, imagine I think something fits a bell curve, right? for like a conversion rate or something like that. A very informative prior is being like, well, I know the conversion rate is 30% for this thing. So I'm going to pick a really sharply peaked bell curve that's almost like a line at 30%. An uninformative prior is flat because it just says, I have no idea what the conversion rate is. So you do have that choice. So yeah, I agree. That is not perfect, but usually for most things, you can kind of guess what the prior is. Absolutely. So this gets into a whole discussion of like confounding variables and things like that. So there's no like, here's the answer for this. So what you usually do with most of these things is you try to separate and eliminate as many confounding variables as you can. That said, I usually phrase this in terms of the change I want to make. So if this is something where it's going to be a localized change, right? Where I'm gonna push a different page to men than I am to women, then I'm gonna split them in the test. But if the page is actually gonna be pushed to both, then I should test on both, right? And then I just need to make sure that when I split the groups, I'm not, for some reason, not like 50-50 splitting on men, women. So it's a subtle art and you will definitely get it wrong. I know I get it wrong sometimes, but you just kind of do the best you can. So where I definitely split, even if we're going to make a change to everyone, is like I know that like our conversion rate on the upgrade page in England is vastly different than it is in the US. So I'm not going to lump those together because I might want to make different changes to those things. So does that kind of answer it?
This may be getting in more for when you give this full bunch of
Yeah. Yep. Gibbs sampling in this case converges faster. Yeah, because Metropolis Hastings for this will just bounce around a whole lot. Gibbs sampling will just converge faster, so it speeds up your computation time.
You said that in your experience, a lot of the time.
Yep. Yeah, so that's actually how we found it out. And it's also how we actually scope. Now we scope these tests and confirm that it's accurate. So when I said like the other Bayesian doesn't work, what we essentially did is Mike McDermott here? So he actually wrote a lot of the code for this and did a great job. He's another data scientist at POF. He's awesome. So what you do is you say, you have two scenarios, right? So we either say like the two conversion rates are actually the same or they're different by a certain amount. And you run the simulation in both cases. So where they're actually the same, we run like 100,000 simulations of this and we test this method, the null test, the other Bayes factor test, and so on. And for each of them, we say, given how we phrase the decision rule, how often does it get it right and how often does it get it wrong? In this case, because we've assumed the two pages are actually the same, getting it wrong is a false positive, right? So that is the type 2 error rate. So what spits out of that computation for like the 100,000 we run is for each method is on average how many samples had to be collected to reach a decision rule and how accurate was the decision. Then you do this reverse. You say, okay, now the two pages are actually different to at least the minimum amount that I care about. I run the simulation 100,000 times and I say, how many times did I get it wrong? That's my false negative rate. How many times did I get it right? That's 1 minus that, essentially. And then how many samples did it take to get there? So what you have is, at the end of the day, a distribution of the number of samples it takes and your ratio of type 1 and type 2 errors. In this case, when we ran it, and we ran it for a variety of scenarios, this was always faster and always more accurate. So win. So the upshot of this is, I know I said this is great, but it does have disadvantages. It's computationally more complicated. You need to know what you're doing. And for some things, it's not going to work. So I'm very skeptical of anyone that says, this is the way you should split test, or this is the best method, because it very heavily depends on your case scenario. So everything, there's no free lunch here, right? Everything has pros and cons. For whatever the case is, you have to pick a pro and a con. And even though I said we really like this Bayesian thing that we came up with, we still use other methods for certain tests where it's practical, where the Bayesian's not going to work or not going to compute in time and so on. So carefully think about what you have. If you don't have a team of PhDs, probably don't do the Bayesian because you're probably going to get it wrong. If you do, go for it. Statistics and testing, it's not. So you can take the formula for a p-value, stick the numbers in, and it will spit out your 97% or 0.03 or whatever it is. The key is the interpretation of that result. If you're getting 0.03, do you actually believe that if you push the change that you'll see the positive thing that you think you are? So be very, very careful. I get this a lot, especially from sort of more business people. They'll say, well, I know the experiment isn't really well designed. We're not really quite measuring what you want, but like you can compute a p-value for me, right? And I'm like, yes, but that's not going to actually tell you anything about how this behaves in the wild. So it's not the right thing to do. And there are some things where you can't measure it and you can't test it, right? If you're a politician and you want to see what a policy change is going to do to your approval rating, you can't be like, well, you half of people, you can now murder one guy a month, but you half of people can't. It's not going to work, right? You can't split test that. So you have to come up with something else. So either find or do the hard work to learn yourself proper experiment design and proper statistics. If you don't want to do it yourself, find someone that does. Please don't just Google split test calculator on the internet and go to the first page you will, because I can't tell you when I was doing this, I just did it as an entertaining exercise for an hour, how many of them are just wrong. Like they make assumptions that you probably don't want to make. They don't account for type 2 errors. They don't do this, whatever it is, they get it wrong. I'm not saying there's not right ones out there, but if you don't know what you're doing, your chances of picking the right one, statistically speaking, are probably pretty low. So if you're interested in some of these methods, I'm going to be kind of giving, I don't know exactly how we're going to break it down, but I'll give one on like null hypothesis testing, how to actually compute a p-value, sample size, how to run the test, and all that kind of stuff. I'll definitely do the Bayesian. I'll probably do the multi-arm bandit. I may or may not do the sequential test because I haven't done it in a while. So please come to those things. Ask me questions if you're interested and so on. So that's basically it. Come bug me. Add me on Twitter, email me, add me on LinkedIn. I'm usually pretty responsive, happy to grab a beer or coffee, that kind of thing. And again, thank you to everyone here. And thank you for hosting me and thank you guys for coming. I really appreciate it.
We have time for questions, so if you have any, Robert over there will be I Love R t-shirt as a handheld for 1 year, but stand within a foot of it.
Felix is going to heckle me now.
I'm gonna give you a bigoted statement and ask for a comment about it. So I don't care whether there's a difference between the two landing pages I'm trying to optimize. I just want to increase the conversion rate of my page. If I make that statement, does some of the mathematical complexity go away?
Do you want to be confident that you've increased the conversion rate in your page?
No, I just want to pick the variant that I want to increase the conversion rate of my page.
Yeah, no, it doesn't, because I know you're trolling, but like the way you've phrased it is, so the key with this is once you make the change, is it actually going to hold up in the wild, right? So you now let it run for a month or 2 months and so on. Is it actually going to be performing better? If you're just like, well, I'm going to push this change to 100% of people and like, oh, it went up 3%. So like, now I'm just going to keep it that way. You don't really know if it went up 3% for any reason that's related to the change or not. And so you don't know if you've actually made the correct thing. It actually could have been that like, had you not pushed the change, your conversion rate would have gone up 5% with the old page just because it's that day. And you've actually taken a 2% hit that you don't see just by making that change. So no, in that case, my answer is no.
I think you were talking about A/B testing versus not A/B testing there, and just looking at the. Is that correct?
In that case, yeah, I was kind of going for that example, but in the same case, like, so you could do A/B testing, but like you're saying, like if I stop the test early or something.
No. You've gone to a lot of care in all of the to take type 1 and type 2 errors through each of the frameworks that you've proposed in your talk.
Yep.
what if you don't care if the 2 pages are equivalent, as in have exactly the same intrinsic conversion rate? What's wrong with picking one and thinking it's better than the other?
Nothing. But there's a big difference between saying they're exactly the same versus like they're not, and the actual change I'm making is negative, but to some amount that I don't know. So again, it's a kind of a sliding scale of like, and we've seen this, like I've seen this before, where like if I compute a 95% bound, like a true 95% bound on the difference in the two conversion rates, yeah, zero's included, but it's a little to the left of zero. So if it's a little to the left of zero, now I could be like, well, p-value wise, they're completely equivalent, but I can't actually guarantee they are. So you usually want to stick with the thing you know. But that said, yeah, there's nothing inherently saying you can't go to the other page. You just won't have a lot of confidence that that change is positive or negative. It's basically saying it's roughly equivalent.
Cool, thanks.
Thanks for the troll, though. Felix and I go to lunch and talk about testing a lot, so I know he's trolling me.
In the lull between questions, we're thinking about going down to Steamworks for food and drink afterwards. So if anyone wants to join us,
Yeah, I need beer.
raise your hand so we know how many people are going to come along. Small group. Okay.
Yes. So you're saying like I want to, okay, so there's two different kinds of multi-testing here. So one is, which we do easily. So let's say I want to test the landing page and the upgrade page. As long as I'm convinced that there's no reason that those tests will like conflict, then you just run them and it's okay. Where it gets more subtle is like I want to run 2 tests on the upgrade page at the same time. Then what you essentially do is you split your traffic. So you say 50% of people that I'm going to choose at random go to test 1, and then I split those people A, B. The other 50% of people go in test 2, and I split those A, B. The important thing is that split itself, the head split, has to be random for every test. So again, you don't want to keep the same 50% of people together throughout series of tests because then you create the herding behavior. So then, yeah, I mean, you up your runtime by 4 or 2 or whatever it is, but you can do that. And we haven't done it yet just because it has nothing to do with the math or the test architecture we have. It's just like our design team and our product team can't come up with enough work changes to actually run them in parallel. But we do have enough traffic in some segments of the site where we could be running like 8 tests at once, no problem. Because a lot of the things we'll find our duration is like less than a day, but we have to run the test for a week because of seasonality. So in that case, you might as well run 7 at once. But we just don't have the design attributes to do that.
So if you run a test and say that the orange buttons are better, another test and say that Helvetica has better fonts, it doesn't tell you that the combination of both is going to be good.
That is correct.
So why would you run 2 different tests rather than not the combination as well?
So I agree with you. In other cases, some people want to make, it becomes like kind of a technical coding thing where it's like one team's working on this, one team's working on that, and it's not that easy to combine. So in that case, you kind of split the difference, and that's what you do. I agree with you because what he's talking about is essentially like, let's say and this is actually a famous example, I think at Facebook or something, where like one team changed the background color and one team changed the font for a test. And there was a group that actually saw the font and background color were the same. And so it just was like a blank screen. So like that didn't do well when they interacted, even though independently, though both tests looked really good. So yeah, you want to avoid that. So the point here is that you can't assume that like one change and another change, that there's no interaction between them. And so in that case, I would run the multivariant. And we have done those kinds of things as well.
My question maybe is more like design related, but let's say you ask your designer to design a button that gets lots of clicks, and your designer comes up with this button with like a flaming fire around it and very clickable and very visible and great. And you have another button which is simple and like similar to buttons that you see in different places, and you run your test and it becomes, you see that based on the data that the one mid flames is actually significantly higher conversion rate rather than the other. As a data scientist, would you go with that button of like a
Uh,
funny?
I mean, I like flames, but
I mean, like, how do you balance the design versus the data you get from like just
so this is
Right.
actually a really good question. And the way I look at my role as a data scientist is it's my job to provide people with the information to then make the business decision. And I'm happy to like weigh in and be like, I think flames are cool, so let's go with that. That said, just because a test is successful doesn't necessarily mean it's the right business decision to make. So, for example, we could run a test where we paywall something that was previously free for half the users and then be like, we're going to test revenue on this. Revenue's going to go up, right, on that thing. Does that mean it's the right long-term business decision to make for the product? Possibly not, right? That then becomes a balance of what do you think you're going to hurt your user base long term for versus the short term gain that you're going to get from increasing that. So I don't regard my job as to be like, this is definitely the right answer. My job is to say, okay, based on the data, here's your potential gains or losses or things like that. Now, do you feel comfortable making that change? And so we've had examples of that where we've run a test, something has looked successful, but not quite enough that we feel comfortable with whatever it's doing to the rest of the site kind of thing. And we go back on that. So again, there's no like right or wrong answer there. It's always a balance between those considerations.
One of the first things you said was that you need a clear defined metric for deciding your test.
Yep.
Doesn't that fly in the face of what you just said?
No, because one is this test is successful and the data is telling you that this is a successful, like the flaming button will give you, 7% higher conversion rate. And that's great.
Okay.
So that's a clear decision rule, right? That's not like, is this test successful or not? That's separate from the business decision of, do you want to go with the test results?
Then how's that then different from, say, your monetization goes up, but your retention goes down? So you can have two metrics, and ultimately you're trying to optimize the bottom line of the company, and you have to kind of make decisions based on several different factors.
Yeah.
And so the test for retention could go up, but the test for monetization could go down.
Absolutely. So that actually is why I said pick one clear metric, because otherwise you do get in that competing thing. So again,
you want to just look at one.
Well, that's why I said you pick one to decide the test, because you need to compute a decision rule or a sample size or something to tell you when to stop the test and call a winner. But you can look at secondary KPIs or tertiary or whatever they are to then be like, well, the test said monetization was up and we're great, but we took such a hit in retention because of this that we don't want to push that change. The two decisions are still separate. Now, you can be more complicated and try to come up with a combination rule where you say, I'm going to weight monetization by this much, find some unit conversion over for retention based on like, well, the number of people I retain should upgrade at a certain rate in the future and they'll pay out at this rate. Write down a complicated function with an uncertainty and phrase the decision rule in terms of that, right? In essence, when I was talking about the revenue test, that's what I was doing, because I wasn't saying the 3-month plan or the 6-month plan was the price of that. We were computing with like forecasting what we expected long-term revenue to be from the 3-month plan versus the 6. And that changes the ratios you want to shift things over with, because the 6-month plan is not worth twice as much as the 3. It's worth like 1 point something plus or minus some amount with a curve, right? And so that changed our decision rule by quite a bit. Yeah, that's a consideration in every single test you run, right? Like if you're making systematic, so all the stuff I'm talking about with type 1, type 2, and so on is assuming your errors are random. If you have a systematic error, Yeah, and that's why we do it with like extremely broad. So like we're more like I always like in this case went with the most conservative method in essence like the highest variance curve for that long-term value. Right? And like yeah, there's no right answer there. And like believe me, I struggled with it for 2 months. Like myself, the other data scientists and a couple other guys, we were like, what about this? What about that? Does this take it into account accurately or not? And we really worked on it. And I still don't even know if we have the right answer. But at some point you have to kind of do the best you can. And in this case, we decided to go as conservatively as we could.
How do you control for
No, and I totally agree with you. Right.
Tommy? How do you control for network effects?
I knew you were gonna ask that. In our case right now, we don't because we've been running relatively straightforward, simple things. As we move on to other more complicated tests, so network effects here are like, let's say I make a change that increases messaging on POF. That looks really good, but actually the messaging I've increased is a bunch of douchebag guys spamming girls like, "Hey babe," and it drives all the women off the site. Like that's a negative overall change for the site. And that's a network effect kind of thing. So like, I don't know is the best answer I can give you. It's something that I've spent a lot of time thinking about and have yet to come up with a good answer. And I've spent a lot of time thinking about it with you and have yet to come up with a good answer. So if you're holding back on me, you schmuck, and tell me what it is.
So if you were actually at the casino in front of the 2 slot machines, what algorithm or what method would you actually use?
I go Bayesian because I think Bayesian is, well, no, I take it back. So it depends what the cost of the slot machines are and how much money you give me. Well, no, the reason for this is like if I don't have a lot of money compared to the cost of the slot machines, I want something that's going to try to guess the right solution as fast as possible and may make an error in a certain direction and try to converge as fast as possible given a certain conditions. And what you can see is given a certain number of trials, again, if you weren't at Chasm's talk, I highly suggest getting the slides for it or something like that. He had some really nice curves showing the different algorithms and in different scenarios, how fast they converge and so on. And they do cross at some point. And so given that, based on like the constraints I have, I would pick the one that I think is going to give me the highest return based on my starting money. So there's no good answer. I like Bayesian because Bayesian's awesome and it's easy to code up, but so is UCB1.
Yeah, I agree. I just created one of those plots like a couple days ago. So I was curious if rope would actually perform similar to just the regular Bayesian or.
Well, rope is not bandit. Right. So you're asking bandit.
Well, any technique that you would use to choose which lever you're going to pull, right?
Well, normally bandit's different because it's assuming that I have a finite amount of money to start with. The other testing methods basically say like, I can run this as long as I want. So if you're really doing the slot machine thing, to make those on equal footing, you'd have to give me infinite money,
right?
Which you don't have, right? Because all of the actual convergence theorems assume infinite money. And it's that the regret function in the limit that you go to infinity eventually converges to 0.
Absolutely. Yeah. Thanks.
They all do, right? He just said that UCB1 assumes infinity for convergence, but all the like stochastic bandit algorithms assume infinity because otherwise there's always some finite correction that says you're not there. Yeah.
How do you do you still do any focus group kind of qualitative testing on top of this? And
Yes.
how do you build that into your process?
So to me, that kind of stuff comes about to suggest the type of changes to make to then test. So we do like, let's say we did a lot of this at POF with our UX person who's now unfortunately moved on, but she was very good at this stuff, where we had people come in or we interviewed people and we said, how many clicks does it, like, can you find this in the app? Can you complete this task and so on? And the ones that were really hard that we thought should be simple informed us, okay, well, maybe we should move this button here. Maybe we should put this on the homepage, whatever that design change that's suggested is. And then that is something that we then test. So the problem with like the sort of focus group research is that your sample size is really small. You know, we brought in like 20 people or 50 people or 100 people. So you don't have statistically relevant results, but it's suggestive of things to try that you can then test on a massive user base. So I think they actually work really well together. Like, I don't spend a lot of time suggesting design changes because if anyone's seen me attempt to do anything artistic, user experience, or anything, I'm god awful. So I have no business doing it. So that's not my role, but we work very closely with the design and product team for those types of things.
Hi. I just want to know. Sorry. I just want to know. How will you control? Or actually, how do you guarantee that your samples are like clean? So in this sense, say you have a login user and versus the non-login users, then and you say you want to test for the conversion rate, then what if you had like a login user somehow they decided to go not log in and then complete a say a purchase? Like how do you like
With a lot of difficulty. So I'll describe a test that we ran, and it's really hard. So we wanted to test different landing pages on the Android app. So we do a lot of native testing. So someone for the first time downloads the Android app, they don't have an account, they want to sign up, and there's like a couple step sign up process to get on the site. So here's the problem with this. So when someone does that, you don't have a user ID because they haven't signed up yet. They're not logged in. The problem though is that not everyone that downloads the app or is not logged in is a new user. So there's two kinds. There's people that just for some reason logged out, or there's people that created an account on the web, then downloaded the app and then logged in. So what I had to do is we had to go in and see so we have a flag that says essentially the first time you download the app and the first time you run the landing page, there's a flag that fires that says this is the first time you've ever run the app on this device. And we also have a unique like device ID that we record per install. So we're okay kind of there. But then I still don't have all the people that like log in or forgot their password or whatever. So the only way to do that is I have to follow their behavior for a few actions and see what they do. So do they complete the sign up process or not complete the sign up process, but stop? Or do they go to forgot my password or log in or do something else? And we actually followed it all the way down the chain and eliminated those people. Was it perfect? No, but it eliminated like 15% of people from the test. And it was really hard. Like it took us a week to do, but it was necessary because otherwise you bias your results, right? The fact that like the landing page for like, and how that impacts like new users signing up, I don't care what it does to someone that already has an account. Or vice versa, like I could do it the other way around.
I'm just wondering how often you actually talk to your users like real humans and then use that to inform like what tests you're going to run.
I don't, because they don't like let me out of the cage kind of thing. Like you don't let the data scientist.
I figured.
Like my girlfriend's sitting there, she going to test. I don't speak to people well. As a company, like I said, we did about 4 months or so of focus groups and user testing and interviews and stuff like that. We also have like a full customer service team that reads all the emails, reads feedback, and we do take that into account. But that's not me. You do a bit, but a lot of the changes we're talking about here are super subtle. It's the kind of thing where like on the upgrade page, we added like a little lock icon to show that your credit card purchase was secure. Most people didn't even realize it. Like there's like a subconscious thing. So what you're talking about, yes. And if we were making lots and lots of major changes, sure. That said, a lot of it, like we've run so many tests, not all of which were successful. So actually I should have said this. One of the important things about running tests is also the ones that don't succeed. And the reason for that is it keeps you from making mistakes. So there's this kind of thing I get with a lot of, especially the business side of the company where like they regard any test that's not quote unquote pushing the variant to be an unsuccessful test. And they're kind of like pissed about it. I'm like, well, I just saved you from making a 5% negative mistake. So that's good too. Learning what doesn't work is as important as learning what does. A lot of the things we've done, we've run so many successful tests that have actually, when they go into the wild and we've checked like revenue's way up, signups are way up, that kind of thing, that we haven't seen that fatigue set in yet. For the amount of people we have, it's really hard for that to do. If you're a smaller site and you're making bigger changes, that could be an issue, and that is something to take into consideration. This poor guy wants to ask a question. Sorry.
Question for you. You have some volunteers to help clean up and put chairs away. Thank you. Come over to the side afterwards.
With A/B testing, I just wanted to know what you do about the problem that the people in Group A might talk to the people in Group B. In other words, you're really trying to test, say, 2 landing pages. You're trying to test a world in which there's only one landing page or there's only one other landing page. If, for example, the one landing page had a different price than the other, in a perfect world where you had the higher price, everybody might think, wow, it's more valuable and you'd get more revenue. But in the world in which you had 2 prices, people might feel ripped off had they talked to.
Yeah, OkCupid got burned for this, actually. Is that what you're asking the question?
No.
Oh, okay, so OkCupid did what's essentially called dynamic pricing, where they charge people in like New York City more than they charge people in Nebraska, because people in New York City pay more for stuff. People found out and they got pissed. In our case, like with the landing page, stuff like that, while we're running, like we haven't done a lot of things where we've pushed like different pages for different people, like once the test is done. And the percentage of people that are like installing the app at the exact same time and talking to each other is probably pretty small. So we don't worry about it too much. And we haven't really done a lot with pricing on the upgrade page. It's usually more changes to things like suggesting this plan or changing the look and feel of the page kind of thing. And again, you would need like 2 people to like actually be in the same room looking at it at the same time to really notice the changes that we're making. So it is, I'm not saying it's not a consideration, but in terms of the pro con of like, when we have a test that's like made us 10% more revenue, to me, the pro of that beats out the con of like 2 people possibly being pissed. Right. But that is a decision you have to like take into consideration. Josh is going to tell me I'm wrong.
No, if I'm going to do that, I'll do it in person when I can enjoy the look on your face.
Yeah. Okay.
But I was actually wondering about some of how you would deal with longer business cycles, because when you're talking about seasonality or certain events, the benefit of something like POF is that you know when those events are going to occur. The sad holidays when people are drinking whiskey. Like with, if you're in a different kind of business, then you have, if you're dealing with a quarter, like, 3 or 4 months or longer, that could be your business cycle. And you have that as a very dependable thing, but you have black swan events where it's like, normal quarter. Oh, the LIBOR scandal happened and we're going to be receiving 20,000 times the volume of traffic.
Yep.
Is there a method that lets you account for that? Oh, and something happened completely unexpected?
I mean,
Or is it
like there's in time series analysis, there's like intervention analysis in theory. It's really hard. For me, if I was running like just a simple like A/B test, I would just invalidate the test, right? I would just say like, this traffic or whatever it is not representative of normal business practices on my site. And so it's not that the test is bad. It's just that like whatever results I'm getting, I have no reason to believe will actually be the behavior like 2 months from now. And that's really what you care about, right? It's not just calling a winner, it's projecting that right thing.
Well, it's just messaging that you might lose a quarter if something happens, and accept that's the business.
You might, right? Or if you think that change is like actually significant. So like in our case, a significant change is like, we released the iPhone app, right? Well, we're not going to take it back. So now like that test is reasonable to run because things are shifting to mobile and we care about that. So you kind of have to make a judgment call there. So like I don't know if they're going to do what I suggested, but I've said multiple times, don't run a test over Christmas. Don't run a test over Valentine's Day, because it's not going to be representative of anything that you would expect for the other like 363 days of the year. So don't do it. Right. But that's not necessarily up to me.
Thanks.
Thank you, Tommy. Awesome talk.